Good morning, I am Devasena. In this lecture, we are going to discuss about coupled circuits, and in detail we are going to discuss about self-inductance and mutual inductance. This topic is present in the subject circuit analysis under the topic coupled circuits. Let us start discuss about coupled circuits. Coupled circuits refer to circuits involving elements with magnetic coupling. If the flux produced by an element of a circuit links other elements of the same circuit or nearby circuit without having any electrical connection between them, then the elements are said to have magnetic coupling. Likewise, circuits with a number of branches are said to have conductive coupling. In magnetically coupled elements, the power or energy transfer occurs through the magnetic flux. In conductively coupled elements, the power or energy transfer takes place through the current. In general, coupled circuits refer to circuits with magnetically coupled elements. Let us see magnetic field representation with a small animation. Here we are having a magnet. We know that the magnet is having north pole and south pole. North pole is shaded with red color. South pole is shaded with blue color. A field is created around the bar magnet. This is indicated in the diagram. See the another way of representation of the magnetically coupled circuits. When the two circuits are placed very close to each other such that a magnetic flux produced by one circuit links with both the circuits, then the two circuits are said to magnetically coupled circuits. This is the representation of magnetically coupled circuits. Here we are having two coils. Each coil is having a voltage. Now alternating source is applied to the coil 1. Because of the alternating source, the current is flowing to the first coil, that is a flux is generated. This is indicated in the representation. This flux links to the second coil, and in the second coil we are having an induced voltage. This is represented here. So V1 is called as the alternating source and V2 is called as the induced voltage. Let us see the pictorial representation of magnetically coupled circuits, how it works. This is the representation of a magnetically coupled circuits. Here we are having an iron core. In this iron core we have two coils. So coil 1 is connected the one side of the iron core and coil 2 is connected to the other side of the iron core. With this setup, virtually all of the flux passes from one coil to the other because it is closely contact. Let us see the another representation. Here we are having two coils. So coil 1 is having a flux. This flux induced in coil 1 creates a linkage with coil 2. So depending on how closely air-cored coils are coupled, only a portion of the flux from the primary links with the secondary. This is represented here. Let us see the magnetic field lines representation with the help of a small animation. And this is an iron core. In this iron core, current is flowing to the circuit. The red color line indicates the passes of current in the circuit, and the green color line indicates the magnetic field lines. Because of the flow of the current in the core, a magnetic field lines are induced. This is called as a flux or a magnetic flux. This is represented in this animation. Let us see about inductor. A wire of certain length, when twisted into coil, it becomes a basic inductor. If a current is made to pass through an inductor, an electromagnetic field is developed. A change in the magnitude of the current changes the electromagnetic field and hence induces a voltage in coil according to Faraday's law of electromagnetic induction. Let us see how the current is flowing in the coil with a small animation. This is the representation of a coil. Now in the coil, current is flowing. Because of the flow of the current, a magnetic flux is indicated. This is represented in the graph. Now current is flowing to the coil. A magnetic flux is induced. This is represented here. Another way of flow of current indication in a coil. And this is a coil. In this coil, the current is flowing, that is indicated in the diagram. Let us see inductance L. The coils having n number of turns made up of various materials and having various sizes are called inductors. The property of a coil which opposes any change in current passing through it is called an inductance, denoted as capital L. Inductance is treated as a circuit element which stores energy in the form of electromagnetic field. The inductance property is measured in Henry's, capital H. Faraday's law of electromagnetic induction. Michael Faraday, a British scientist, stated two laws of electromagnetic induction on the basis of various experiments he performed with permanent magnet and a coil. Faraday's first law. Whenever the number of magnetic lines of force linking with the coil or circuit changes, an EMF gets induced in that coil or circuit. This is indicated in the small animation. Here we are having two magnets. In between those magnets, a magnetic lines are created. If this magnetic lines or circuit changes, means an EMF is induced in this circuit. This is indicated in the animation. CS waveform changes whenever if the flux linking with the coil or the magnet cuts. Faraday's second law. The magnitude of the induced EMF is directly proportional to the rate of change of flux linkages, that is flux into number of turns of coil. This is indicated in a small animation. Here we are having a coil. To the coil, an indicator is here. Now we are inducing EMF in the coil by keeping the magnet inside the coil. Because of the magnet, an EMF is induced due to the induced EMF, current is flowing to this circuit. This is indicated in the animation. Let us start discuss about self-inductance. Consider a coil having N turns. The initial flux linking with the coil is phi suffix 1. Therefore, initial flux linkages is equal to capital N into phi 1. In time interval t, the flux linking with the coil changes from phi 1 to phi 2. Therefore, the final flux linkages is equal to capital N into phi 2. The magnitude of EMF is proportional to the rate of change of flux linkages. That is, V is directly proportional to N phi 2 minus N phi 1 the whole divided by T. Therefore, V is equal to K into N phi 2 minus N phi 1 the whole divided by T. With K as unity, to get units of capital V as volts, d phi is the change of flux, dt is change in time. Hence, d phi by dt is the rate of change or flux. That is, V is equal to N into d phi by dt. Now, as per Lenz's law, the induced EMF sets up a current in such a direction so as to oppose the very cause producing it. Mathematically, this opposition is expressed by a negative sign. Thus, such an induced EMF is mathematically expressed along with its sign as V is equal to minus N into d phi by dt. This property of the coil which opposes any change in the current passing through it is called self-inductance or only inductance. Self-induced EMF. According to Faraday's law, due to the rate of change of flux linkages, there will be induced EMF in the coil. The EMF or voltage induced in the coil due to the change of its own flux linked with it is called self-induced EMF. Mutually induced EMF. If the flux produced by one coil links with the other coil placed sufficiently close to the first coil, there is induced EMF in the second coil. Such induced EMF in the second coil is called mutually induced EMF. Let us see the mutually induced EMF with the help of small animation representation. This is an animation. Now consider that we are having a coil. The coil is connected in the supply voltage. Because of the supply voltage, a current is flowing to the first coil. Now, a second coil is taken very close to the first coil. Due to this, the EMF induced in the first coil gets induced in the second coil also. Because of that, the load that is connected to the second coil will get glown. It is indicated in the animation. Thank you very much for listening to this lecture. For further updates, kindly subscribe this channel. If you like this video means you can share this video with your friends.